That's really, really exciting. We've been using quantum mechanics to predict all kinds of things and use it for like probably 100 years. Most basic thing of quantum mechanics, we don't understand how it works.
How did we get there? How did we figure out that our old model was incorrect and more likely it's like this?
In hindsight, it doesn't make sense.
But it will be once we have these energy sources and our quantum phones.
Yeah, now I have to silence you.
Welcome to the 8th episode of the Kimudo podcast. My name is Kim, and this is Udo.
Hello.
Today's episode is a deep dive into quantum mechanics, a topic that you and I both have not discussed yet on the podcast, really. But we are both quite interested in it. You know a lot more than I do. I don't know anything. So the way we've structured the episode today is we've written up some topics that I have heard, or different things that I've heard about quantum stuff, but that I intentionally didn't go and find out the answer and read about, so that I could have this discussion with you today, Udo. And from what I understand, you have prepared a bunch of answers for these questions, yeah?
Yeah. But by the way, why are you interested in quantum mechanics?
Because it seems to be every now and then you have some paradigm shifts, and quantum mechanics seems to be one of those paradigm shifts where all of the traditional physics seems to break down and not make sense anymore in quantum mechanics, and I don't know why it's so wild. So yeah, I can't wait to talk to you. It's gonna be a fun episode today. So, leading into the first question, how did we know we could make a computer out of quantum shit? Whose idea was that, and who worked on it, and why?
Holy shit. So quantum mechanics goes back like over 100 years now, okay? And somewhere in the 70s, people started to think about quantum computing. And especially two people, Yuri Manin and Richard Feynman. Feynman is a very famous physicist. But before that, we kind of have to acknowledge that quantum mechanics has not always been used. In fact, it was quite controversial back in the days, and to be honest, today it's still kind of weird to think about, because you said earlier that you don't really understand quantum mechanics. In fact, physicists always say like no one in the world understands quantum mechanics.
I've heard that before. And the people who say that they understand it are usually bullshitters and liars, huh?
Yeah, exactly. That's basically exactly the point. Like, there's two types of people: the people that don't understand quantum mechanics and the people that lie. Okay. Back to the quantum computing. As people understood a little bit more about quantum mechanics, they applied quantum mechanics to the atoms and molecules and chemical reactions. I mean, if we look at an atom, for example, the typical picture that people have is like a nucleus in the middle, and then like electrons around it that are just circling around the nucleus. I bet everyone has seen these types of pictures that are representing the atom.
Yeah, it's quite recognizable, I would say.
Yeah, it looks pretty cool, to be honest.
Mm-hmm.
And it reminds you of the solar system, like just like the sun in the middle and then the planets around it. And obviously the planets have like circular orbits or elliptical orbits. But the thing is, this doesn't apply to atoms or molecules, because
why?
People realized, physicists realized that it doesn't make sense, because there's something you have to know about electrons. Okay, when they move or when they get accelerated, to be more precise, they emit energy, they radiate. Okay?
Mm-hmm.
So when you have an electron on a circular orbit, like here, then it should always emit energy. And this means that it loses energy. The energy has to come from somewhere, right?
Right.
So the electron slows down, and if it slows down, then it also means that it falls into the nucleus. So this basically means like that atoms are not stable. If you look at it
They want
in
to
the
collapse on
classic,
themselves.
yeah, they're always collapsing. That's the old model, basically. And that's one reason why quantum mechanics had to be invented, or where quantum mechanics plays a role. Because if you try to explain atoms in the classical way, it doesn't make sense. These things collapse. They're radiating, and then the electrons collapse into the nucleus, and then nothing would work. You and I wouldn't be here. Computers wouldn't work. Actually, no matter in the universe would be stable at all. So people couldn't.
What does stable mean? That it doesn't collapse on itself.
Yeah, exactly. Our atoms gladly they don't collapse on themselves. Like I just don't. I don't accidentally disintegrate or so or vanish. But yeah, that would
Speak
be
for
kind of
yourself,
sad.
bro. And how do we
solve this? Or
how did we get there? How did we figure out that our old model was incorrect and more likely it's like this? And
there were a couple of hints in the beginning. One of the most famous ones was Albert Einstein, who figured out that light is not continuous, but the energy of light is in little packages that he called photons. So that's what physicists call light is quantized. Light has little quanta of energy. Okay, so you don't have basically a laser or a ray that you can zoom in infinitely, but if you zoom in strongly enough, then you would see basically like little pixels, little packages of pixels of light. Okay, and that's what Albert Einstein got the Nobel Prize for the so-called photoelectric effect, which also showed that light is quantized, that it comes in little packages, in little quanta. Okay?
Okay.
And this information that light comes in little quanta or packages, if you apply that further into different problems in physics, that's what physicists did back in the days, then you end up with quantum mechanics. Just like when Albert Einstein had the idea that the speed of light is constant, okay, he applied that to different problems in physics, and this led to him creating the theory of relativity, which is a paradigm shift.
Yeah.
It was really crazy. Because one of the things that the theory of relativity says is that time is not constant, space is not constant, but they warp. They are really connected to each other. They're actually one and the same in a so-called four-dimensional space-time, which was a huge paradigm shift. Okay, back to the atoms. Now we will have another paradigm shift, which is that atoms and electrons don't come in precise circles, or they don't have like trajectories, but the way you can imagine it is that an electron basically like a cloud, okay? And sometimes you can measure it, and the moment you measure it, it appears like it's just like a particle. This was completely mind-blowing for people back then.
Yeah.
But that model explained why atoms are stable. Because when, like the quote-unquote trajectories that people, like physicists, could see, that's explainable with that new model of like clouds, basically, electron clouds. And this then resulted into the molecular orbital theory, MOT. And after that, people did calculations to try to understand molecules and their the way they bond with each other. Yeah, they try to understand that further. And the thing is, these bondings are quantum mechanical effects. So back in the days, they tried to use classical computers to simulate quantum effects. And in hindsight, it doesn't make sense. Like, if you want to simulate quantum, then obviously you should use quantum, right? And that's what Yuri Manim and Richard Feynman independently said.
Yeah. Came to
What?
conclusion.
Yeah. Why do we use non-quantum stuff to simulate quantum stuff? Like, it doesn't make sense. And that's where the idea of a quantum computer started.
So it was first theorized that there's got to be a way to build something that is quantum to some stuff.
There was a need. There was a need for a quantum computer because classical computers weren't capable of simulating these quantum effects on a molecular level.
And then, so what is what is a quantum computer compared to a traditional one that we know?
Okay, so in a traditional computer, you have bits like zeros and ones. Okay, for example, if you look at a black and white image, and you have like white dots and black dots. The white dots are ones and the black dots are zeros. Okay, so you can clearly see that. But in case of a quantum computer, you have something called a qubit, which is not only 0 and 1, but it's 0 and 1 at the same time. Something in quantum mechanics which is called superposition. Something can be in two states at the same time. And probably a lot of people have heard about Schrodinger's cat.
Yep.
Have you heard about it? Yeah, yeah, you're
No.
laughing already.
Yeah, but explain it. I guess it's always interesting. If you've never heard it, it's fun to listen to. So you want to go through Schrodinger's cat real quick?
Yeah. So Schrodinger had this thought experiment, which is called Schrodinger's cat, and it goes like this: that you have a room, a closed room with a cat inside, and in that room is the cat and also a radioactive source. And radioactive decay is of statistical nature, and it's quantum. So in quantum mechanics, you have superposition, which means like the radioactive material, it can either decay, it is either decayed or it's not decayed. And if there's a superposition, then it's decayed and not decayed at the same time. And then the same thing applies for the cat. That's the thought experiment. So as long as you don't open the room where the cat is in, or the box, then according to quantum mechanics, you could say that the cat is alive and dead at the same time. It has not been killed by the radioactivity, and it has been killed by the radioactivity at the same time. And when we look at this, it doesn't make sense at all. That's what Schrodinger was trying to point out, that quantum mechanics doesn't make sense at all.
It's not intuitive to our crappy garbage brains that evolve over thousands of years.
Exactly.
It's just we are not good at conceptualizing. That's why I think this topic is so fun, because everybody hears the word quantum in the news all the time, but what does it really like kind of mean on more than the simple and basic level? I find it super weird. Like, yeah, sorry, I'm not gonna move
You're not
ahead.
the only one. You're
But
not the
yeah.
only one. Even physicists, like just as we said earlier, that either you don't understand quantum mechanics or you're lying, because like no one really understands quantum mechanics, and even Einstein had problems with it, and he said to about quantum mechanics that there's something missing about quantum mechanics. He called it a theory that is incomplete because of the next thing that we will talk about, which is the measurement problem. So you have this weird thing called superposition, where two states can be present at the same time. Like the cat is dead, that's one state, and the cat is alive, that's another state. But according to quantum mechanics, these two states can be present at the same time. So the cat is dead and alive at the same time. But when you open the box to see if the cat is dead or alive, you only see one of the two. That the cat is either dead or that the cat is alive.
Traditional
You never see it,
physics.
yeah, exactly. Traditional classical physics.
Yeah.
Exactly. And the understanding that's missing is how do we get from this quantum mechanical superposition, where two states at the same time can be present, to classical physics? That's the measurement problem. Like, what happens during a measurement? That's what we right now, as of 2024, don't understand.
And this is called the observer effect.
Observer effect, or the measurement problem.
Or the measurement problem.
Yeah, no one really knows what's happening during measurement, and that's really, really exciting. Like we've been using quantum mechanics to predict all kinds of things and use it for like probably 100 years. Okay, but the most basic thing of quantum mechanics, we don't understand how it works. It's just like we use our phones every day. Okay, we know how to turn it on. We know how to use the apps inside, but we have no idea how the inside of the phone does all of that. That's basically the measurement problem. Like the measurement problem is the inside of the phone, and we're just using the apps in the phone. Okay, like we can use it every day. I can open up WhatsApp or YouTube or Google to search something, right? But I don't understand how the interior of the phone does all of that. Just like physicists use quantum mechanics every day to do some calculations, okay? But they don't understand how a measurement works. Basically, the most fundamental thing of quantum mechanics.
And so we realized we need superpositions, and there was a need, you said, for it. What kind of new stuff did we theorize that we would get out of making quantum computers and all this other stuff? Like, how do we know that compared to a traditional computer, right? Every year we're just sticking more CPU and cores into them, right? And then the clock speeds and core speeds go up, and then we stick more RAM into it, and then we exponentially move up, according to Moore's law on computing power that way. But clearly, this paradigm shift of quantum computers, we needed the superpositions, like you're saying. I understand that now, but what did we figure out we needed to come out of having these two positions on and off at the same time that would then eventually lead to like AI? It's mind blowing that you could go from theorizing something to building a computer out of it that then AI, uses to make better answers somehow. And how did we get from the theory of gravity to like how do we get from theory of there has to be something called like obviously it's a a wave function collapse, and obviously we should build something out of it that then we like how, what was the need, and how did that come?
Okay. That was kind of a lot of questions and
Yeah, just talk to
sentences
me.
at the same time.
Yeah, give me everything. Teach me.
Okay. One thing after the other. First, what are these superpositions used for? So, with a classical computer, okay, you have the bits 0 and 1, okay? So if you have 0 and then you have 1, you have 2 bits, okay? But the advantage of a quantum computer who uses qubits is that one qubit can have the information of 0 and 1 at the same time. So in the classical computer, you needed 2 bits to do what a quantum computer does with only 1 qubit. That's the advantage. That you can do a lot of calculations in parallel. And that's really important for training AI as well.
It's interesting. So
That
how come that doesn't just mean that you've doubled your computing power? How come it means quantum paradigm shift,
because it's
Because of
not
this,
it's
'cause
more
of
than
the
doubling.
positions. Yeah.
It's
How?
literally more than doubling. I crunched some numbers. Okay. The Bitcoins, for example, they have right now they have a hash rate of roughly 620 exahashes per second, which is, let's say, a huge number.
Yeah, that's also my understanding of it. I was thinking like a Trumpian, huge.
Yeah. And so let's try to visualize what is a exa hash. So kilo hash would mean 1,000 hashes per second. Okay.
Kilo meaning 1,000. Yeah, 10 to the third meaning 1 and 3 zeros.
Yeah. Mega means 1,000,000.
10 to the
After that,
sixth.
yeah. After that, it's giga, which is 1 billion. And I mean, nowadays we're past giga. Where usually people have like terabytes on their SSD, right?
Yeah, they do.
So that's the next level. Okay.
Okay, and giga is 10 to the 9, meaning 1 and then 9 zeros behind it. Just to put this in context, okay? And then tera?
And after that, tera, just like in terabyte SSD.
Teraflops.
Yeah, or teraflops. This is 10 to the 12. And we're still not at exa level. Because exabytes is 1,000,000 terabytes. 1,000,000 times the thing that is already huge as hell.
So now exa is 10 to the 18.
Yeah. And
1 and 18 zeros behind it.
Yeah, and the current hash rate for Bitcoin is 620 times 10 to the 18, which means a huge ass number. For Bitcoin, it means this huge number of 620 exabytes, 620 billion trillion calculations per second in order to mine one Bitcoin. Okay.
Yeah.
And if you
oh, just that? 1 second easy job, dude.
Yeah, I can do that in my head, man. And that's when you use classical computers. Okay. If you use a quantum computer with a Grover algorithm, you could mine Bitcoin like a quantum computer would need 1 day. Okay, a classical computer would
1,000
need
years.
19,660
Yeah,
years
yeah, called it.
for what? Yeah, for what a quantum computer would only need 1 day.
Got it. So it's not
It's
double.
crazy,
Yeah,
and it's not double as efficient.
it's
It's
to the
even
X
more
power
efficient.
of. Yeah, I have
Yeah,
no idea.
because the scaling is square root. So the the bigger the number gets, okay, the more efficient quantum computer gets. Just imagine that in the future, like the more we mine Bitcoin or the more we train AI, okay, the more efficient quantum computers get. That's why big companies like IBM and Google are investing so much money into research on quantum computing.
Yeah, because the potential upside of unlocking some of this computing power, while it's expensive to be a pioneer in the it's very capital intensive.
Yeah, exactly.
So you need
Uh,
these big ones. But it is the advantage of these big companies to do this, right? Not everybody can build these huge models because of the amount of capital it costs. But if you're one of the big giants, that's your advantage. That's your first mover's advantage, that you can be unlocking these key algorithms or whatever for their companies.
yeah, it's not only algorithms but technology, like the
Yeah,
hardware.
yeah,
Because like it's one thing to like copy the algorithm, but it's
sure.
another thing like if you have the algorithm but you don't have the hardware to use the algorithm,
Yeah.
then you can't do anything. Yeah, that's the huge advantage that these big companies have. But just like all things, just like back in the days with the dot-com bubble, right?
Mhm.
Um, the internet back then, websites were pretty much buzzwords. Okay, so right now we have to be careful as well. Like maybe we are overhyping things. Like
Yeah.
there was definitely a lot of potential in the internet back in the days. Okay, but there were some things that needed to be done first, like fundamentals, basically.
Yeah, like
To and
security to take online payments.
yeah, exactly, like online payments or widespread internet or high enough bandwidth to play videos, for example. And maybe we
Yep.
will see the same problem. Like probably we will see the same problem in quantum mechanics. That there's some problems that hinder the development of quantum computing that we don't see right now.
Mm-hmm.
Yeah, bottlenecks that we will discover in the coming 10 to 20 years or so. But after that, it's going to be crazy.
I think it already is with all these AI things coming out there. I mean, there's so many AI models now. You can get an AI search for almost anything and then put AI behind it, and you'll find there probably is someone who's built some kind of model that where it helps you with whatever you've got. So it's crazy.
Yeah.
We use them in big part for this podcast, actually. Huge proponents because they make our work on working on this podcast streamlined in a huge way. So yeah, amazing. And like you're saying, I don't understand what we're even doing. I just, like everybody else, say like a .com bubble. .com bubble. It was always like, do you have a .com email? Or do you have a .com business email? Business URL. Now it's like, do you have an AI? Does your company use AI?
Did you find a website that says like there's an AI for it.com or so?
Yeah, yeah. It was something like that. It was yeah. It had a list of all of them too. I still need to go through that list actually. Fun stuff. Okay. So if we had enough computation power in the future and information and knowledge about quantum mechanics, could we then predict where that electron appears? And I'm referring, of course, to, you're gonna have to probably go back to explain a little bit, but we wrote down here left side, right side of wall thing. So could you explain first what the electron appearing through a wall means, and then after that, if we had enough computation power and in the future, and information of knowledge about quantum mechanics, could we then predict where the electron appears? Like, I guess what
Yeah.
I'm going with this question is that would we eventually have, like we have Moore's law with traditional computers, would we have that for quantum computing power where eventually it's going to unlock, I mean, I guess anything, right? Like
Wait.
encryptions.
Slow down.
Okay.
Write that question down.
Okay.
Like,
I'm gonna write that down,
Moore's
and then
law.
you get the first part. Okay.
In the meantime, I will explain
Perfect.
the first part.
Sounds
So,
good.
what Kim was referring to about left side, right side of the wall, there's an effect in quantum mechanics, which is called quantum tunneling, where the setup is like this. You have an electron, or you could use any particle that is small enough, basically, and then you shoot it at a wall. Okay, so in the classical sense, for example, if you have a wall and a football, then you shoot the football against the wall, what happens? It's gonna bounce back, right?
Yeah.
That's what we expect. Okay. In quantum mechanics, that's not the only thing that can happen. So in quantum mechanics, if you shoot an electron against a wall, okay, yes, the electron can bounce back to you, but it can also just go through the wall. This is called tunneling, like tunnel through the wall. And just imagine that in real life. Like, just imagine you're playing with your soccer ball, you're kicking it against the wall, but sometimes your soccer ball just appears on the other side of the wall. It just went through the wall, not because you broke the window.
that was more my childhood. But but then okay, so I had a counter for you, and I think it's important that we get this on the podcast, right? Because for me, my question then was, okay, how could it go through the wall, right? And what I led up with that was, and I'd like to hear your take on this, recorded on the podcast, because I think other people are going to think the same thing. How could it go through the wall? And the way I was thinking about it is, if you're looking at atoms, for example, we know that most of the between the atoms are space, right? So actually, the human body is mostly made out of technically of space, because that's what it is between us ourselves. So if you were like tiny enough, and for example, and you could theoretically like fly through fast enough, wouldn't it be sometimes rare instances where your small then vehicle could then go through technically a body then, imagine, because atoms are so far spaced apart? Is it the same with the wall? Sometimes it's a quantum whatever and a quantum atom or whatever you call it, it's so small that sometimes it's going to bounce against the wall, because even though it's so tiny, it's just going to happen to bounce against and come back. But sometimes it's going to go through the wall because it is moving so fast and it's so small that it technically sometimes is going to that's just what's going to happen. You shoot enough qubits or whatever, you shoot enough quantum at enough walls, eventually some of them are going to go through the wall. That's just by sending enough, which you can, and you aren't you? Isn't that what it is?
Okay. I understand your analogy,
Yeah.
but one thing that you have to keep in consideration is the way you imagine it is that there's basically electrons or balls or particles flying around your nucleus, right? That's how you imagine it, like the classical way of looking at a atom.
Yeah, that revolves around each other. Yeah, that's what I think.
Yeah, and there's a lot of space in between, and
yes.
that's true. But these electrons also have a electrical field, which means they are forces. Just like when you have a magnet, okay? Like the magnet doesn't have to. Two magnets don't have to touch each other.
Yeah, they repel or attract each other, regardless.
Exactly. So they can still build a wall. Okay, if you basically have a wall of magnets, even if there's space in between each magnet.
Yeah, sure. Yeah.
Okay, and that's basically the way you have to imagine it. Okay, if you have a couple of magnets lying next to each other, and then you try to shoot another magnet in between the space between the wall of magnets. Okay, yes, there's space in between, right? But there's a force field,
Yeah.
the magnetic force that goes
Will impact.
against it.
Yeah.
Exactly, and that's what physicists mean by a wall. The wall of this force field. It could be the electric force, it could be the magnetic force, but this kind of force field wall that prevents the particle to go through the wall. And this works even though there's a lot of empty space in between these things. Okay.
And then so how come some make it through?
That's the next thing we will get into, which kind of has to do with superposition. So the superposition that I explained earlier was with a cat, Schrodinger's cat. It can be dead and alive at the same time, right? And for qubits, it's 0 and 1 at the same time. There's also a superposition for electrons or small particles in general. They have a superposition of their position. So if you kind of have GPS coordinates of your electron, right? Then you could have on the x-axis a value of 1 nanometer or so, 2 nanometer, and so on. Okay, that's the position of your electron, right? In a classical sense, the electron only has one position. Okay, but in quantum mechanics, due to superposition, it can have many positions at the same time.
Yeah.
Can be at position
and can I just
one.
describe what you're kind of drawing up so people can understand? Imagine if you're drawing an x-axis and a y-axis is what he's done. And then imagine if you're drawing a kind of a classical almost bell curve. Then he's filling in the bell curve. He's talking about everything inside of the majority part of this bell curve, which is called is that what's called a wave, I guess?
Yeah, that's
Okay.
that's the wave function.
Yeah. Okay, continue.
Okay, so the electron can be found in not only at position 1 and 2 and 3, but it's at position 1, 2, 3 at the same time. It's kind of like when you look at a bee, for example. Okay, when a bee is flying, then you look at its wings, and then you kind of just see this fuzzy little thing, which is kind of smeared out, and that's kind of similar to superposition, right? You can't really tell where exactly its wings are, the wings of the bee.
Yeah.
It's somewhere in between, like position 1, 2, and 3. So, but you could, if you take a picture and the shutter speed of your camera is not high enough, then like you kind of see that the bee's wings are everywhere at the same time.
Yeah, in motion.
A little bit. Yeah, exactly. And that's kind of similar to the electron, but it's in all of these positions at the same time. But there's some positions where it's more likely to find the electron, and there are other positions where it's not very likely to find the electron. Okay?
Just like a bell curve.
Yeah. Just like a bell curve. It looks just like a bell curve. Okay? And if we basically shoot this bell curve at a wall, we can see that one part of this bell curve is on the left side of the wall, and the other part of the bell curve is going through the wall.
Mm-hmm.
So this means that there's a tiny probability that the electron just goes through the wall.
Yep. And that it could be, at any given moment, observed at that side.
Yeah, exactly.
Yeah, it's so wild. It's so crazy to think about it that way. So, okay, and my follow-up question, can I go to the follow-up question?
Yes,
Did we
yes,
finish? Okay.
yes. Yeah.
And the follow-up one was then could then, if we had enough computation power in the future and information and knowledge about quantum mechanics, could we then predict where the electron appears? So, yeah, my question was then, I guess, is it about the specificity and how sensitive the instruments are? Because you're saying, like, for example, in the bee, with the slow shutter speed of a camera, we will not catch which position it is in, right? But that's a lack of our instruments. So my next question then, I guess, naturally has to be, okay, is that what quote unquote superpositions are? Is it just a lack of specificity? What happens if we had more sensitive computers that then all of a sudden, again, if you zoom in harder, we realized, oh, they're not in superposition, because for X thousands of insert tiny time unit here, micro millisecond, something tiny, okay, whatever. We realized, oh, actually they were not both open. They were both, one was closed and one was open, and there's a lag or a flicker or whatever. Would that then break down everything, or is this not possible?
It's not possible. That's what the huge paradigm shift was that quantum mechanics caused. That's
that it is a fact that they are both open at the same time, and it doesn't matter how. If we got more sensitive equipment and somehow removed observer status, we would not get different data. We don't think.
Yeah.
Interesting. Okay, continue. Why? Sorry, I didn't mean to interrupt you.
That's what the data shows. There's a famous experiment called the double slit experiment, which basically goes like this. Like you have a wall with two slits. That's why it's called double slit. And then you shoot electrons through these two slits. Okay. When you measure what's on the other side, then you get what is called an interference pattern, which is really weird because electrons are, we think of them as particles, but in this situation, they behave just like a wave. Like if you imagine ripples in water, for example, then you've probably seen something similar as well in water, that the water waves or water ripples, that they kind of interact with each other, and at some points they completely destroy each other, where the water's flat, and at some other points they kind of enhance each other, where you can clearly see the wave. And that kind of pattern is also what you see in this double slit experiment with electrons. But then when physicists measure the electron to see if the electron went through the left slit or the right slit, then the interference pattern just vanishes. And then there's just a normal particle pattern. Like if you have two slits, then the electron can either go through the left slit or the right slit. And then on the other side, you would see like two possible ways where the electron could have landed. Okay, two stripes basically. Okay, so this is really weird. As soon as we observe the electron, and it changes its behavior. It goes from classical to something else. So it goes from particle to wave, or the other way around. And what I'm trying to say with this is, just like the bee example and its wings, we would expect when we zoom in more, when we zoom in enough, that we would see the details on how things work. But it turns out that that's not what happened. It just breaks the interference pattern. It breaks the superposition. It breaks the quantum mechanical effect. That's why when we measure this double slit experiment, there are two possible outcomes. One is this weird wavy interference pattern, and one is just these two stripes of particles.
Yeah, just like you would imagine if you shot paintballs through two different slits, you would imagine there'd be a spread, but the spread would be limited only within the two angles from that could be produced from the slits. So yeah, it makes sense.
Yeah. So yeah, that's basically the paradigm shift, where we try to zoom in more, but when we zoomed in more, it just broke the experiment, basically.
Yeah, doesn't that mean it's a shitty experiment, or what does that mean? Is that proof of something then?
Yeah, tell that to Einstein.
Hey, Einstein, are you stupid? Anyway. Okay, so then could we predict where the electron appears if we had good enough quantum computers?
As of right now, we don't. We couldn't. Even if we have better ways of measuring things, I think it's not about measuring finer and finer details, zooming in more. It's about understanding quantum mechanics more. We, as I said earlier, there's this thing called measurement problem. We don't understand what happens when we measure a quantum particle, and that's something that has to be understood in quantum mechanics. And after that, we can see what's going on when we measure the particle.
How do we know? Talking about the zooming in and zooming out of the world, if you will, how do we know there aren't smaller particles then? Didn't we used to, tell me if I'm wrong, but didn't we used to think that atoms were the smallest thing in the universe, and then we realized no, there are smaller things? How do you think that there's another smaller things, even a whole different world yet again,
That's a good question. I think this goes to the topic of reductionism, where like everything that you see can be reduced to smaller and smaller and smaller
Bulbs.
subsystems or particles. It's like we humans are made out of cells. The next subsystem is molecules. The next subsystem is atoms, and then the next subsystem is quarks, and so on and so on. Like how deep does this go?
Yeah.
Right.
And thank you. Quarks was the word I was missing.
Yeah. I think we don't know what's smaller. We have no idea how small this goes, and that's why it's extremely important for scientists to develop more tools for them to measure things that are even smaller than we can comprehend. And this was literally the Nobel Prize in Physics in 2023, which is for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter.
Oh my goodness. For experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. Yeah, say that 10 times quick. Yeah, what a dummy, another dummy. I love it when people work on things I can't read, I'm so stupid.
This basically is zooming in a lot.
Mm-hmm.
And let's take a look how much we're zooming in right now. Like everyone can imagine what a millimeter is when they take out their ruler and then try to measure how big it is.
Yeah. Yeah. We all know. Yeah, true. Example perfect. Moving on.
That's millimeters.
Unlucky. Then you have micro after that. Yeah.
Which is 10 to the minus 6. Even smaller would be I mean, micro, that's literally the size of microchips, I guess. That's why they call it micro.
Yeah.
And the level below that, deeper, is nanometers, which
Yeah.
is roughly the size of atoms.
Yeah.
And then if you go even deeper than that, then it's pico, which is 10 to the minus 12.
Yeah.
And then you're still not there yet. You still have to zoom in 1,000,000 times more. You
Yeah.
literally like
Yeah.
if you have an atom, if you have an atom, then you literally have to zoom in 1,000,000,000 times more to get to
So
atometer scale.
it's an exponential problem again.
It's even smaller than we can comprehend, and that's the level that these amazing scientists are working on. And these are very fundamental tools that will be very impactful in the future. At first, it kind of sounds boring because they're kind of just zooming in a little bit more, right? I mean, 1,000,000,000 times more than
A little
an
bit.
atom.
Yeah.
Yeah.
That's the biggest reduction of a man and woman's degree ever. Just a slight zoom in of time there.
Yeah. But these tools are extremely important. It might not be that flashy. It might not be cool to talk about. Yeah, we're just zooming in a little bit more than before, than anyone else before in the history of humanity. But we will be able to see a lot more things due to what these physicists have discovered,
Yeah.
the tools that they developed.
Yeah, shout out these physicists. If you want to come on the podcast, we'll definitely make you lose some IQ, but we would love to have you on. That would be fantastic. Can you imagine? Hey, how does one study an attosecond pulses? Oh, nice to meet you, Kim. You sweet, sweet, stupid man. You do this. Yeah, amazing.
Yeah, and that's in physics, but there's a lot of fundamental things in other sciences as well, whether it's chemistry or biology or so. Do you know what a scanning tunnel microscope is?
No, tell us.
Or back in the days, people used optical microscopes
Yep.
to study.
Like biochemistry, maybe, and things.
Yeah.
Yeah. Yeah, looks like a
And
regular microscope to me. A lab microscope.
yeah, and with that, people could see like cells, neurons, and stuff like that.
Uh-huh.
But after that, there were scanning tunneling microscope, which could zoom in even further. And with scanning tunneling microscopes, people were able to see not only cells, but also DNA. So you can see on the molecular level,
The helix
like
structure. Oh yeah, the chromosomes
yeah,
and
what the chromosomes look like,
wow.
which is really insane.
Yeah, it is.
And this scanning tunneling microscope is literally taking advantage of quantum mechanics, the thing that we were talking about earlier with quantum tunneling.
Uh-huh. How does it do that?
So, in quantum tunneling, an electron can go through a wall, right?
Yep.
And the thicker the wall is, the less likely it is for the electron to go through the wall.
Yeah.
Okay.
Yeah.
So, what this electron scanning tunneling microscope basically does is it shoots electron, tons of electrons, and basically an electron beam through the sample that we are
Scanning.
scanning. Yeah, thank you. And the thicker the sample is at that point, the less electrons will be detected. So you can make an image out of that by scanning through the whole sample, like just row after row, from left to right, row after row.
Mhm.
And then it's kind of like what are these called? Audio recorder? So,
Yeah, it looks
yeah.
like they look like topographs to me. What you're showing me, topographs? Yeah, see, like a map.
Record labels. Is it that? Yeah,
Yeah, a
exactly.
vinyl.
Yeah. Vinyl. Exactly.
Uh-huh.
It's basically the same. But if these vinyls, they have this. I don't know what it's called. But it's basically like a pin. It's kind of like going through the vinyl plate uh, and touching and feeling where it's high and where it's low.
Yeah.
Okay, that's basically how this scanning tunneling microscope works.
Right.
When
Yeah,
it's
and it looks
going
like a
low after low.
topograph on this scan that we're looking at right now. He's showing.
Yeah, that's one other example of groundbreaking things that are that improve our fundamental understanding, which is really important for science. Even though it doesn't sound as flashy as, for example, two black holes collapsing into each other.
So I was thinking, if we had enough computation power in the future, okay, I'm sure I'm not the only one who's thought about this. Could it retroactively unlock every single encryption we have that we're currently using on these traditional or classical computers?
Oh, this is an interesting topic because quantum mechanics or quantum computing makes you capable of doing a lot of computations at the same time due to this thing called superposition. And there are some algorithms that are only possible on quantum computers, which is, for example, Shor's algorithm, SHOR algorithm, and that's something that can break the typical RSA encryption. And a lot of things are encrypted with RSA. So what hackers or people on the dark web do is they're just downloading important information. This could be government documents or documents from the CIA or so. They're just downloading them, even though all of that data is encrypted, okay? Kind of useless right now. They're hoping for that in the future, when quantum computers become a thing, that they can decrypt all of that data at that point with Shor's algorithm.
What do you think that will unlock?
I'm very excited about the things that the CIA has to hide.
How ironic would it be if, because of quantum computers, it unlocks all these alien files and whatever because it was on some stupid server that wasn't really quite probably where it should have been, that had an internet connection or something, and then it turns out that also how, if you believe in aliens, here's cancel podcast number 1. Oh, one of the podcast hosts believes in aliens, but if there are aliens, wouldn't they also be using like quantum probably technology most likely then to do everything?
Aliens might be so advanced that we have no idea what they even use. Like just like a monkey has no idea what a phone is or how it works or what
Yeah.
software is.
Or what a
Like
satellite is, or that it even requires a satellite to function.
yeah, exactly. Like that might be the level of difference between us and aliens.
Yeah, like trying to explain an iPhone to an ant.
Yeah, good luck with that.
Yeah, for sure. We might not have the capacity until we evolve into whatever bionic thing we're going to be when we blend into our technology. Can we see anything else? Obviously, quantum.
Okay, this scanning tunneling microscope was one example. Yeah, that scientists use. So one example would be LEDs. The way LEDs work is that on a microscopic level, there's something called the band gap. And when electrons jump the band gap, then they emit light, which depends on the width of the band gap. So the bigger the band gap, the more energy that light has. So blue light, for example, has a lot of energy compared to a red light. So a blue LED has a bigger band gap.
Right, I've seen this before. It's kind of like if you're thinking about a ripple in the water, the hertz or the frequency of how fast it like reverberates back and forth. If that's not the right terminology, I apologize. But yeah, you can see that would mean closer or more distance rings or bigger ripples versus smaller ripples.
Yeah, and that's higher frequency.
That's
And
higher
blue
frequency.
light
Yeah,
has higher frequency than red light.
makes sense.
Yeah, that's one example. Another example is MRI scans.
Magnetic resonance imaging.
Yeah, which takes advantage of the spin of, I think, hydrogen atoms in water molecules. And spin is a property that only exists in quantum mechanics. So there's no classical example or analogy for what spin is. It behaves a little bit like the rotation of something sometimes, but there are some properties that are nowhere else to be found. So it's only a quantum mechanical thing. Yeah, these are two examples.
Interesting. Okay, thank you. Do you have some fun quantum facts you can throw at us? Are there any kind of fun, either confusing or exciting ones?
Okay, there's something called the Casimir effect.
Say that again.
Casimir effect.
Okay. What is it?
So, it's when you have two metal plates in vacuum. Okay, if they have a certain distance or lower, then
Proximity, really, right? Proximity.
yeah, exactly. Um, when they suddenly start to attract each other, and in a classical sense, like you can't explain that. Like, where the fuck does this energy come from? Where does what kind of force is that actually? And in a classical sense, you can't explain that, but in quantum mechanics, you can explain it. It's kind of a weird phenomenon. Uh, it's not something that's every day. Like you would have to be an astronaut to experience that in perfect vacuum, or you have a fancy setup in your backyard. Another cool thing is superconductors, which is conductors like if you have a copper wire, for example, and you send electricity from one end of the copper wire to the other end, when a little bit of energy is lost. That's converted to heat energy. That's why your phone gets hot when you use a lot of computation on your phone, playing AAA games on your phone or so. Yeah, that heat energy gets lost, but that's because every copper wire or like wires in general have electrical resistance. But for superconductors, the resistance is zero. So the electricity you can send through superconductors, there's no energy loss in between.
And no heat then generated.
Exactly. So if you had like superconductors in your phone or in your computer instead of copper wires, then there would be no cooling needed because the computation just happens without the generation of heat. This would be really crazy for supercomputers in the future. Like right now, like obviously you have some processing unit, but on top of a processing unit, you need heat regulation, some kind of ventilation system, for example, or you cool it with water. So that takes up space, right? So in the future, when we use superconductors, and all of that space that would have been used for cooling elements, we could use for more computation instead. So you can squeeze in even more computation for a smaller amount of space.
Is this how we power our personal quantum computers and AIs in the future?
This might be how we will have AI training on your phone. I mean, you can have a bit of AI training on your phone, but like with the current computation power, like it takes ages. Like,
yeah,
it takes way too long. That's why so many companies are buying so many NVIDIA chips to create their own supercomputer to process all this training data.
Right.
Because like your phone, the microchips in your phone are not enough.
But it will be once we have these energy sources and our quantum phones. Do you think we will have quantum phones in the future? Perfectly cool to the touch.
Perfectly cool.
Imagine.
Just imagine your phone doesn't work during summer because it's too hot.
Imagine. Yeah. Or imagine if you drop your quantum phone and it's like, imagine all the little small parts in there would get damaged from just gravity. You drop your quantum phone. That's muerte for that phone, probably. Gone are the days where we have Nokia 3310s, you know?
Just imagine you get a notification when your phone vibrates, and then that destroys all the quantum properties in your phone. Repairing that one costs $2,000.
What if your phone is both vibrating and not vibrating at the same time?
Schrodinger's phone.
At all times. You know what that is? That's like when you get a text message on your phone, or when you hear a sound and you feel like your thigh or whatever, because you're feeling for your phone to see if it was you who got that message. That's the quantum phone. It'll be both vibrating and not vibrating at the same time, and it'll always feel like a phantom itch. Just like one of those things where you're like, was that my phone?
It was and it wasn't.
It both was and it wasn't, yeah. Oh yeah. It's like when you send those WhatsApp messages and then you go, oh shit, you delete the message, but they've still got the whole message in their notification, even if you delete it. So as long as they don't like accidentally remove the notification, you can still read the whole message. All you gotta do is swipe down. But if you click on WhatsApp, it'll say message deleted. So it's Schrödinger's WhatsApp. The message is both able to be read and it's gone at the same time.
So I guess there you have the answer. Like, we have quantum phones already, right?
Absolutely, yeah. So, what do you think? Would it be possible to get it into a phone format? Why yes or no? Show your reasoning.
Well, my first question would be, what do we need that for?
All the massive computation power. That's what we need it for, because we'll figure out how to generate like AI. Well, we already have figured out how to start making generated AI movies and AI videos and things on demand. You know, you make a video as you're wanting to watch it. Like, we'll definitely have it. It'll be just like, you know, what you're saying now, I think, to me, sounds like when you have the typewriter, you're like, why would I need a computer? I got a typewriter. Because it's better, bitch, okay?
Well, you have to think about it as it's better in some situations.
Mm-hmm.
It's just like when you compare.
But don't you think that's for now? It's for some, but don't you think just like, I don't know, Bitcoin, they started building all this other coin that then you could start using, like they had code inside of it, right? The Bitcoin you could entangle, what was it called?
The decentralized dApps
a non-fungible token and things, right? You came up with different technology. Wouldn't it just be the same? That that's what we think for now because we're monkeys and we don't understand what quantum even is. But if you have a higher being, he'd be like, "Oh, idiots, just unlock this, that, and the other." And then you have many worlds and teleportation all of a sudden or something. I don't know.
I think quantum computation in phones, like for me, like maybe I'm just a monkey, but it doesn't make that much sense. Where it makes more sense though would be VR glasses, because you want as much computation power in as little space as possible in VR glasses. So they don't feel like these giant goggles that you have on your head that weigh too much. But it would be really great if they just feel like normal glasses. Okay, if you couldn't even tell the difference between glasses and VR glasses, that would be insane. So
Yeah, it's true. That would be a game changer. I'm 100% in.
yeah, and what I'm imagining
I
is
don't even
like
care. It's gonna scan my retinas and send that, information over to other companies. Updated every second. Your data will belong to Google. Anyway, continue. Joking, just joking.
it belongs to Google already.
Yeah, allegedly. Anyway, continue.
Cancelled.
Number 2.
Yeah, just imagine having way more computational power for your AI in virtual reality. This means that you could, for example, have a AI generated world generated right in front of you in real time with your VR glasses. Okay, it sounds kind of like a lot of buzzwords right now, but for example, there are AI video generators that can create incredible scenes, which look pretty realistic. Okay, just imagine they use these kinds of video generators in real time when you're looking around.
Oh my god.
With your glasses. So, like, if you're looking to the left, then it instantly prompts a scene that would fit to the thing that you see or that you want to see. So the prompt would be like, yeah, I want to be at the beach right now with a beautiful sunset. And then you look in front of you and you see that a sunset. And then if you tilt your head or look to the left, then you see the rest of the beach. And all of that gets generated instantly.
With no lag.
Yeah.
With perfect pixels.
Yeah. So that's what I'm thinking. So I personally wouldn't use that in a phone. I would definitely use it in VR glasses.
Yeah. That would be really interesting.
Just
Could we
imagine all the games that are possible in the future with that.
Oh, stop it. I can't wait. I can't believe we're so old. We were born long before AI became a thing, because it's in the future, Gen Z and everybody right now, they're all using AI. So if you're not using AI, you're you're kind of falling behind, I think, already. Which yeah, you should check out for our episode 4 if you're interested in AI. We talk more about that in that episode. I wanted to ask you, can we ever feed quantum computer perfect data? Or do you think that data is always just going to scale to like smaller levels until technology achievement unlocked figures out what the next quote unquote quantum computer is? What do you think about that?
I think this comes down to our understanding of quantum mechanics. Like, we don't understand it enough right now. We don't know what what a measurement is, what the solution to the measurement problem is. That's why Einstein called quantum mechanics an incomplete theory. So even more data wouldn't help. It's just like AI, where yes, more data will make your AI better, but at some point you hit a limit and you have to change the structure of your AI for it to perform better. For example, you have to add more hidden layers into your neural network in order for it to have a better understanding. And I think that's kind of similar to your question and quantum computing. That we have to add more layers of understanding of like what is really a measurement, and are there hidden variables in quantum mechanics or not? And after that, we can see like where will it lead us. So perfect data or more data is not necessarily the answer.
So what you're saying is there's a chance. Okay, I understand. Did we answer that? I don't think we answered what it would cost in energy to have a quantum phone. How would it like?
Yeah, just like a real politician, I deflected that answer by saying I wouldn't put quantum in a phone.
Yeah, exactly. And then I was like, wait a minute, I've been duped. I have to circle back.
Gosh, yeah. Now I have to silence you.
I would it just suck all the electricity out the wall, just trying to charge that thing. I just imagine like you're plugging in your quantum phone into the wall, and it would need like a small nuclear reactor to power it. It would just make the whole lights in the house flicker, kind of like it did back in the day.
The whole neighborhood would be like, "Oh, Kim's charging his quantum phone again."
A whole block goes out for a second, comes back. But is that what you think? You think it would be impossibly expensive in energy, right?
Well, that's what I'm saying. That we don't know yet. We don't understand it enough.
Mm-hmm. But quantum computers are quite energy intensive right now, as is. No, they're saying AI, for example, is very non-environmentally friendly, right? Because it's not. It's a very extremely heavy computing task to send AI queries, and the more complex they are, the more costly it is to Mother Nature, right? Or am I not correct?
I have a different analogy. Have you seen the predecessor to computers, like mechanical computers?
No, this is interesting. What's this called? A Z1 Rechner?
Yeah, that's in German.
Yeah, a Z1
Yeah.
computer. Replica of
Yeah.
Z1 in German Museum of Technology in Berlin. Ich bin ein Berliner.
Yeah, exactly. I think
36,000 metal sheets, 1 ton, or
yeah,
2,200 pounds for our American friends.
this computer weighed a fucking ton.
Yeah, literally. I get it.
Yeah, and what was the CPU capable of? 1 hertz.
1 hertz, one
What?
frequency.
So what?
Or yeah,
What is your CPU capable of? How much
uh,
CPU computing power do you have? Like mine is like 2.2 or no, maybe.
Oh, unlucky. Mine is a bit faster. Okay. Let me see right now. I'm opening it up. Okay, my computer as it reads right now, I have 4.17, 4.8. It's dropping a little bit because I opened up Task Manager, but yeah, say 4.20, 4.15, something like that. Between there, 15 on the lower
What's the
end.
unit? Gigahertz, right?
Gigahertz, right? So giga
Giga.
meaning how many again? Go back to your thing.
Oh, wait, kilo is 1,000.
Yes.
Mega is a million.
Million.
After mega is giga, which is billion.
Billion.
So you have
My
4
computer
billion
has
times.
computations, right?
Yeah.
Times each core, correct? Or
Yeah, times each core.
and I have 8 cores.
Yeah. So the point is like you have more than 4 billion times more computation power than that mechanical computer from 1938.
That's absolutely crazy.
This thing weighs a ton, literally a ton, and it was huge as fuck.
Yeah.
And that's what I'm trying to say. That there will be paradigm shifts in the future, just like in computation, that will change the game completely. So back then, this mechanical computer was obviously mechanical, but then they changed to electronics.
Yeah.
So instead of like
Mechanical, you had
mechanical gates,
electrical.
you have electrical gates, and
Mhm.
this enabled modern technology to go way smaller than with mechanical computers. And these kinds of paradigm shifts are necessary to do, for example, quantum phones, if there will be a use case for that, or quantum VR glasses. And yeah, my opinion is that you need these level of paradigm shifts in the future to enable that kind of technology. And having a quantum phone that needs like really electricity consuming cooling, that would be the same as trying to build a supercomputer with mechanical that is built of mechanical computers, where like 1 hertz of computational power is like 1 ton in mass. Just imagine that.
Sheets.
Yeah, just try to do that.
Oof.
Yeah,
I'm
and
surprised it says right there that it's driven by a mechanic. It's yeah, an electric motor of a vacuum cleaner. I'm surprised that it's strong enough to make that thing work. Like I would have thought it would have been like at least like a moped, you know, like a horsepower or more, probably.
yeah, true. Now that you mentioned it.
Yeah, it's 1 ton after all. It's quite a bit of mass.
Yeah, yeah. I mean, the parts of it are way lighter, probably. Just the total is 1 ton. And yeah, instead of like moving mechanical parts, electronic parts are or electronic gates are open and closed to have your zeros and ones in modern computers. Okay, and if we apply that way of thinking to quantum phones, okay, then I think in the future we need something that doesn't require much cooling. So
Yeah.
right now we need tons of cooling to maintain stable qubits in quantum computers. But I mean, there's some quantum probably going on in our brains, and the brain is way hotter than quantum computers. So apparently it's possible. We just don't know how yet. And there's one theory that I think is very, very interesting by Roger Penrose.
Roger Penrose to you.
Sir Roger Penrose, who won the Nobel Prize in physics. I think was about black holes. And he has a partner called Stuart Hameroff, and the two of them have this theory, what they call orchestrated objective reduction theory, or OR, and that's in that theory they try to explain consciousness, and Sir Roger Penrose explains it with quantum mechanics and gravity. That's his approach. And yeah, in the next coming decades, we will see where it will lead us. I personally think that's a very promising theory. So right now, like I talked about the measurement problem earlier, and that theory kind of tries to explain what a measurement is. And the way it's trying to do it is gravity is what's causing the collapse of the wave function. So it causes the superposition to go into classical mode, basically, to choose between one of the two states. And he has done some calculations on it, and he proposed experiments, and the experiments are running in the background, and yeah, we will see what the results of these experiments are. And let me go to a little bit more detail on this theory. So I said that it's trying to explain consciousness, and what Sir Roger Penrose says is that when a wave function collapses, okay, that's a moment of consciousness, a very small moment of consciousness that he calls proto-consciousness. It's kind of like one of your skin cells is not you, but a lot of your cells make up you. Okay. And this skin cell is basically like proto-consciousness. A lot of proto-consciousness can form eventually a full consciousness.
A human.
So yeah.
A bunch of gut biome or a bunch of skin.
Yeah, or neurons in your brain. If there's a lot of these proto-conscious moments in your brain, then that's what makes you conscious. And Sir Penrose's partner, Stuart Hemroth, has the proposal that the consciousness takes place in tiny parts of the cell called microtubuli. And what he has identified is that there are some proteins in microtubuli that have something called a benzene ring. Okay, like
octagon, I guess.
1, 2,
Is it
3,
octagonal?
4, 5, 6. Hexagon. Yeah. And there's something you have to know about this, because this is basically quantum mechanics, which is very stable. Okay. Have you ever seen the way chemists draw their molecules, like something like this?
Yeah.
There's a carbon atom.
Carbon atom.
This is
Yeah.
a carbon atom.
Is it a
and
hydrocarbon, maybe?
Yes. That's a hydrocarbon, and this H stands for hydrogen. Okay.
Yeah.
Then one line is just a simple bond, and 2 lines is called a double bond. Okay. Yeah. These double bonds, they don't really appear in that way in nature. Okay. Where these bonds are, they consist of electrons. Okay. And they're kind of going through. So these benzene rings, you can imagine it as hexagons, and each vertex of the hexagon is one carbon atom. And in between the carbon atoms, there are either single bonds or double bonds. Okay, and you can kind of have 2 different bits here. Okay. This double bond could move here, this single bond could move here, and this double bond can move here, and so on. Okay.
He's just moving all of the one step to the left in the chain of connection.
Yeah, exactly.
What he's showing with the mouse.
Basically, if every connection of these carbon atoms, if they kind of rotate like clockwise, and you have a different formation, and this different formation is basically a different bit, or the same bit just with a different information. Okay, if you say this, the thing that you're seeing is represents 0. Okay, like the bit that represents 0, and then if you rotate it by 90 degrees, or
it would be a 1.
Yeah, exactly. It would then be a 1. Okay, and these kinds of structures, these benzene rings, they are found in many amino acids, actually.
Tryptophan.
Yeah. If you look up the structure, you can also see these these benzene rings. And these microtubuli, they have a lot of these structures, and that's the hypothesis, basically, that's where the quantum source basically is. Okay, and there are these two possible states. One is the normal state, basically, and one is the rotated state, which and these two states can be interpreted as ones and zeros. Okay, but there's also the superposition of it, which is called
Both.
delocalized. If someone wants to go deeper into that, delocalized electron. Yeah, and in tryptophan there are these kinds of delocalized electrons of the benzene ring. Okay, and that's not the only thing where we find that.
Here we go again. Your favorite molecule.
Yeah. Which one is it, Kim?
Is it the DMT molecule?
It's a DMT. Yeah. DMT. Yeah. DMT also has these benzene rings, and that's basically the connection. So the microtubuli, they consist of tryptophan. These tryptophan molecules have these benzene rings. Okay, that's basically the normal state of mind. Okay, but because DMT also has these benzene rings, it can have an effect on the quantum source of our brain, quantum source of our consciousness, which many people record. They will tell that after they take DMT, that they kind of have a higher level of consciousness, a higher level of understanding.
Connectedness, right?
Yeah.
Yeah, destroying of ego at times, and yeah, it's really interesting. I was wondering too. We wrote this down. Maybe you can remind me of how this relates to quantum anything, but we wrote it down so that we could discuss this on the podcast and not talk about it before ahead of time. But so you're gonna have to help me out with this one. But we wrote, why does light travel at the speed of light, and why is nothing faster? ... Unless. And you wrote, this is what Einstein called spooky action at a distance.
Okay, yeah. That's another thing that was confusing for Einstein. Because and even now, if we look at it, it doesn't make sense basically. But first of all, I have to explain why things can't go faster than the speed of light. Okay. For example, if you have a rocket, right? If you put more energy into the rocket with more fuel, for example, then the rocket goes faster, right?
Right.
You can't do the same for light. You can't put more energy into light to make it faster. We were talking about LEDs and blue light and red light earlier, and the difference between blue light and red light is that blue light has a shorter wavelength compared to red light. That's because the shorter the wavelength, the more energy is in that light particle, is in that photon. Okay, that's why the shorter you go, like if you go even shorter than blue, then you will have UV light. And that has so much energy that it even damages your DNA. That's why you get skin cancer when you get sunburn.
We get ripped apart.
Yeah.
Shredded.
The DNA gets destroyed and causes mutation.
Scary. Where's sunlock? Let's go to another question.
Yeah.
Quantum hyperparallel algorithm. This means quantum computing speeds up AI training. And I wrote how. What is quantum hyperparallel algorithm?
So the advantage of quantum computing is that it can calculate in parallel very, very fast compared to classical. We know that the difference between classical computers and quantum computers is that classical computers have bits and quantum computers have qubits, and qubits can have two states at the same time. So basically, a quantum computer can make multiple computations at the same time if the quantum computer is set up correctly. And in when you train AI, when there are a lot of training processes that happen at the same time. Like if you ever saw AI training simulations, then it's basically AI trying a bunch of different things at the same time. And it's
and if it continues, then it views that as a success, and it just keeps on moving all these iterations at the same time, right?
Yeah. And if you want to get into more detail, training an AI is basically means matrix multiplications. So if at some point we figure out how to use quantum computer for matrix multiplications, then we will have a very, very powerful tool to train AI in the future. That's basically the computation that is needed. That's the computation that is done when you're training AI.
And to run all these simulations, it's very capital intensive.
Yeah. And if you can cut that cost, then it's probably millions of dollars that you can save.
Wow. Yeah, it makes sense. It's expensive whenever it's a new tech. It always comes down in price eventually. Do you think that quantum computers eventually are going to be able to break down Bitcoin and things? Do you think there's any like worry there with cryptocurrencies and quantum computing?
It's kind of an arms race.
That's never good.
So
I mean, if it means going to the moon, then yeah, it's a great thing. But okay, what kind of arms race is going on?
So if other people are going to use quantum computing to mine Bitcoins faster, then I will use quantum computers as well to mine Bitcoins faster. So at some point, yeah, everyone will just switch over to using quantum computers instead of classical computers to mine Bitcoins. And that's the mining part, okay? Another part is when you own Bitcoin, you have something called a private key, and that's obviously something you have to keep private. But with Shor's algorithm, which is a quantum algorithm, you can break encryptions more easily and then steal someone else's Bitcoin. So quantum computing has basically quantum computing in Bitcoins or cryptocurrencies in general basically have these two connections. One, that mining will go faster. And the second thing is stealing someone's private key, which is their access to their Bitcoin wallet will go faster as well.
Right. So it might be that the game changes. It might be that with the way that computing power works, it's faster to like hack everybody else's stuff and get them than trying to mine it yourself from scratch, perhaps.
Yeah.
So is there a quantum encryption coming up then?
Yeah, has to.
And is that being worked? Is there one already?
I don't know that. Next question.
This is the last question. All right. We are done, he says. Instead of answering, he wrote GG on the screen. I think he forgot he's on a podcast. We will end it here. Thank you so much for listening to today's episode, and we'll see you on the next one.
All right, bye-bye.